It looks like another student email made it in past the spam filters. I wanted to read this one as well because it does ask a relevant question. It begins, Dr. Orbis, in that really long video where you introduced the coupling patterns, you went on and on and on about how hydrogens are coupled and they split one another. And you even showed us how a deuterium how the deuterium spin states split a carbon signal in CdCl3 solvent. But that got me to thinking, shouldn't normal hydrogen split carbon too? If a carbon with one hydrogen has one hydrogen on it, shouldn't it be split into a doublet by the two hydrogen spin states? Shouldn't a carbon with two hydrogens on it be a triplet? Every carbon spectrum you've ever given us shows us the carbons looking like singlets. So what's going on? Are you lying to us? WTF? Signed, another student. Oh, and P.S. Love the shirts. Now, I must admit, I enjoy it when a student ends a message like that by asking me, what are the facts? Because it tells me that they're deeply interested in the answer. And the student is exactly right. The hydrogen spin states should show up in our carbon spectra. And so I want you to take a look at the moment at this particular spectrum. This is our dear friend methyl ethyl ketone. And what I've done is I've just zoomed it in on the 0 to 50 ppm range. So I've left the solvent peak off and I left the ketone peak, the ketone carbonyl peak off. And we're just looking at the ethyl group and then the methyl group on the other side of the carbonyl. So take a look at that one for just a moment and appreciate the loveliness and beauty that we've come to expect out of NMR. Now take a look at this spectrum. I assure you, this is exactly the same tube, run at exactly the same time. It's the exact same sample. But my, what a different looking spectrum it is. I want you to notice in this thing, there are quartets. There is a triplet. Even it looks to me like the acetone contaminant down there has been split up into something. The student is exactly right. The carbons do couple to hydrogens that are attached to them and give all of the coupling patterns that we would expect to see. So here are the two spectra together for comparison. And I want you to see that the centers of these things, either the singlets in our regular normal appearance spectrum or the triplets and the quartets in this strange looking spectrum here, the chemical shifts are exactly the same. They line up with each other very nicely. So it's time to kind of grasp and understand, by default, an NMR instrument, when it acquires a proton, when it acquires a carbon spectrum, will acquire it in what's called proton decoupled mode. It's a way of acquiring the carbon spectra as if the hydrogens that are attached to each of those carbons aren't even there. The technical process is called decoupling, and all of the carbon spectra that you've seen up to this point, the ones that have all the carbons looking like singlets, are proton decoupled spectra. So nobody's been lying about it, but that is a fact that really hasn't been talked about and hasn't needed to be talked about until now. It does the proton decoupling by essentially shining in radio frequency energy tuned to the protons while we acquire our carbon spectra. So when I tell the instrument I want to do a carbon spectrum, what it will actually first do is turn on the radio frequency generator at 400 megahertz, the proton frequency. Now, instead of shining them in and listening for or trying to figure out which frequencies got absorbed, it just continuously, not blast really, but shines in 400 megahertz radio frequency energy. That has the effect of taking every one of the protons in any molecule we have in there and forcing them to oscillate between all of their possible spin states very rapidly, about 400 million times a second. What that means is then the instrument acquires a carbon spectrum while all the protons are oscillating between all their spin states. In the 1 second of time it takes us to acquire the carbon, or at least one pulse of a carbon spectrum, the protons that may be attached to those carbons have oscillated between their spin states so often that what the carbons will essentially, quote unquote, feel is the average. In other words, a signal that may be, because of one proton attached, be a doublet, make that proton oscillate between its spin states so much the carbon will feel only the average. It will collapse to a singlet. And that's how we decouple the protons from the carbons and acquire our normal carbon spectra. So why do we do it? Why do we want to do this to our carbon spectrum? And there's a couple of very, very good reasons. Remember, it's a darn near a miracle that we can actually acquire carbon-13 spectra at all. We have the natural abundance issue with carbon. We have the smaller magnetogyric ratio problem, making the spin state population differences, which already, let's face it, suck when you're dealing with proton, even worse when you're dealing with carbon-13. If we did not decouple the protons that are attached to every carbon, we would take these really weak signals and chop them up into more pieces and spread them out over the spectrum. Look at the thing here. I mean, the quartet is spread out very wide. There's actually a large coupling constant between protons and the carbons they're attached to. Look at the signal-to-noise ratio of the two spectra. The normal carbon spectrum, the one with the singlets, the decoupled spectrum, that one was acquired in only 16 pulses. The coupled carbon spectrum, it's much noisier, but it was acquired at 128 pulses. It took a lot longer to get that spectrum, and it still has a much worse signal-to-noise ratio. Now, we did lose information by doing that. We lost the fact that this carbon is split into a quartet, telling us it's a methyl group. That carbon is split into a triplet, telling us it's a methylene group. Yes, that information is lost when we decouple. But then that's why God invented the depth experiments. Okay, maybe not, but that's why we use the depth experiments. That they give us that information back and still present the spectra with the highest signal-to-noise ratios we can get all the carbons as singlets. In depth spectra, they may be up or down, but they're still singlets. Take a good look at this close-up of the methyl group at the end as part of the ethyl of methyl-ethyl ketone here. This is an extreme close-up of the quartet signal at 8 ppm. And when you look at it carefully now, my gosh, do you see a quartet of triplets staring you in the face? If you are not just feeling a little fluttery seeing that pattern, then you really have no soul in this. That is just the most amazing thing. I'm really curious to know where that would come from. Well, we'll have to think about that later. Continuing on our effort to introduce coupling and coupling patterns and then immediately start talking about decoupling, what we've talked about so far in the decoupling area is heteronuclear decoupling, essentially acquiring your carbon spectra as if the hydrogens aren't present there, aren't attached, by making them oscillate between their spin states so much the carbon signals simply collapse to the average of all the spin states of the protons out there. There is another type of decoupling that can be very useful in certain situations. It's called homonuclear decoupling, and it's most commonly used to simply decouple one proton or group of protons from another. In order to show you how this works and how powerful it can be, we're going to use one example molecule, simply one pentene, a relatively simple molecule that has a rather intriguing proton NMR spectrum. So here's the structure of the molecule, and it has labels in there for groups A, B, C, D, E, and F that we're going to be using when we see the spectra in just a moment. So here's the proton NMR spectra of pentene, and it has all the different chemical shifts you would expect to see, all the upfield peaks here away from the double bond, and then downfield peaks between 5 and 6 pp, around 5 and 6 ppm for the alkene peaks. It has a proper number of groups, the integrated ratios. All look just like we would expect them to. It's a very nice looking spectrum. I want to show you a close-up of the upfield region for a moment, the area between 0 and just over 2 ppm. Here we have groups A, B, and C, and we see almost exactly what we would expect to see. The methyl group is this lovely triplet. The group C over here is a quartet because it has 2 protons from group B, but also the one over there vicinal to it at group D. And then here in the middle, group B, showing that very lovely sextet pattern we would expect with 5 neighboring protons and having all the coupling constants the same or nearly the same. Now take a look at the close-up of the downfield region, the alkene region of this molecule. Now here things are a bit more interesting, I would guess. Here we have coupling patterns that are considerably more complex than we see in the upfield region. And it's no huge surprise. Look at the position of proton D for a moment. This proton is trans to another alkene proton, expected to have a large coupling constant, cis to another alkene proton. They're not going to be equivalent to each other, so there's 2 separate doublet influences. But remember, proton D is also vicinal to the group of protons, the 2 protons at position C. And so I'm going to propose, and then we're going to prove, that this very lovely, just absolutely exquisite pattern that we see here at 6 ppm is actually a doublet of triplets. It is proton D under 3 separate influences. It's just a stunning pattern. And as we go through some of this, if I break out into tears of happiness at looking at some of the patterns that we'll see, just forgive me. It's unavoidable when you're doing this kind of stuff. Now I want to show you a proton decoupled spectrum of pentene. Now remember when we did heteronuclear decoupling for carbon-13, I told you what we do is we essentially shine in all the possible radio frequencies for proton. In other words, that collection of around 4,800 hertz centered at right around 400 million hertz, 400 megahertz, and make every one of the protons oscillate so rapidly between their spin states we just see the average effect. We're going to do something similar in the homonuclear decoupling, but instead of putting in radio frequency energy aimed at all the protons, when you do homonuclear decoupling, you aim it at just one proton signal, and then essentially reacquire the spectrum as if that one proton or that one group of protons wasn't even there. What I'm going to show you then is the homonuclear decoupled version of the pentene spectrum, where when we decouple at group C, right around 2 ppm. So this is the one that is being decoupled. This is the group that is oscillating between its spin states so rapidly the remaining protons in the molecule only feel its average effect. In other words, we acquire a spectrum as if group C were not even there anymore. In order to see how this works, first take a look at the upfield region. Now this spectrum looks quite a bit different than it did when we looked at just pentene itself. you see a distortion right at 2 ppm. That is the decoupling pulse. And then you see this quartet here for position B. Remember, in the original spectrum, it was a sextet. It had 5 neighboring protons, but with position C gone now, being decoupled, it now only has 3. The 3 protons back there at group A. And so the sextet has collapsed to a quartet. Notice the protons at group A seem to be unaffected, and they are just too far away, 5 bonds away from the protons in group C, and so this pattern, this lovely triplet out here, the most upfield triplet of the bunch, is completely unchanged. Now that's the upfield region, and that's nice, but it really gets interesting when you take a look at the changes that have occurred when group C is decoupled here in the downfield region. So if you thought that was slick, here's the downfield region, and notice what has happened to our friend Proton D. That gorgeous but complex pattern is now a doublet of doublets. Oh, it's just so beautiful. The doublet of doublets, a trans coupling constant to proton F, a cis coupling to proton E, the vicinal coupling back to proton C is gone. You also see a bit of a simplification in protons E and F. They are actually subject to very long-range coupling all the way back to group C. Remember, pi systems can do that, and it's a subtle effect, but it is observable here. But it's proton D that I really want to focus on here, to really see the changes, how this complex pattern has become a doublet of doublets. Since we removed group C, 2 protons, it lends a little bit of credence that lurking inside this complex pattern at group D is a doublet of doublets of triplets. With the triplet part removed, all we now see is the doublet of doublets. And you can take this doublet of doublets and make the software label in hertz each of the peaks and start extracting out the coupling constants. And it's illustrative to see that here with the doublet of doublets. This is the doublet of doublet coupling tree. The trans coupling constant here, the difference between these peaks is about 17 hertz. The cis coupling constant comes out at 10.3. So here they are, all laid out very nicely here, showing the doublet of doublet coupling tree overlaid on the actual doublet of doublets from the spectrum. This gets us 2 of the 3 coupling constants for group D, the doublet, doublet, triplet. 2 of them have been extracted, and now we're going to go after that 3rd one. So here is the full doublet of triplets for group D. This is the completely coupled spectrum. And what we've done here is overlay the doublet of doublet coupling tree and then added on the triplet component as well. I've only done it on one side because this does get complicated looking, but you can kind of see how each branch of the doublet, of the original doublet, proton D to proton F, splits into a second doublet, proton D to proton E, and then each of those splits into a triplet, where some of the signals actually overlap each other. The triplet coupling constant is a classic vicinal, just under 7. It comes out about 6.65 hertz here. And finally, the ultimate in trying to understand and measure coupling constants is to extract them out of the spectra like we've done with the assistance of a homonuclear decoupled spectrum, and then to actually go and simulate that spectra and see how well it matches the actual measured spectrum. There is software that will do this, and you can also find websites that are very clever and will do this. And I have a link to one that I'm using for this demonstration on the course website. Here is the simulation and the parameters I used in the actual spectrum. Now, in one of the things I want you to do in this module is to actually play with this on your own. So I'm not going to go through the details here of how I set that up, but here's a picture of it, and it's included in all the spectra that are also available on the course website that goes with this video. But here I want you to see the simulated spectrum and the actual spectrum. And what I've done, I've had to stretch the graphics a little bit to make it work out right. But what I've done is I've put them so that they have the exact same width and they're showing the exact same region of the spectra. And in blue is the simulated, in black is the actual measured spectra, and they match up with each other beautifully. So that set of coupling constants that I use to generate the simulation, 17 Hertz trans coupling constant, 10.3 Hertz cis coupling constant, 6.65 Hertz vicinal coupling constant, reproduces exactly the actual pattern or measured. And thus gives me a good deal of confidence that this pattern we see for proton D is indeed a doublet of triplets, and these values of the coupling constants are indeed correct. Excuse me. It's just such beautiful stuff. Homonuclear decoupling. We use it to simplify complex coupling patterns. We can use it to see which protons are coupled to other protons. For example, if you have a spectrum, a fairly complex spectrum, and you hit the signal, say, at 4 ppm, and you see the signal at 2 and the signal at 5 ppm suddenly change, but all the others remain intact, then you know exactly, which multiplets are adjacent to, proximate to, the protons at 4 ppm, say. And it also can be used, as we have done here, to extract out from a fairly complex coupling pattern the actual coupling constants that generated that pattern.